name is Boicey. I am a core technologies developer at the FemtoStar project, and today I'm going to be giving a talk titled FemtoStar Helium, Fault-Tolerant Computing for when 2 plus 2 equals 262,148. Most of the time you'll just see my slides, but I can pop in anytime I want to. So let's get right into it. Over here. So a little about FemtoStar to begin with. Our slogan is satellite communications done differently. We're a global community organized online who's developing a satellite communications network. The most important thing about our network is that it's what we call open infrastructure. That means it doesn't make any strict distinction between a user terminal and a gateway. It can make a connection between any two terminals that can see the satellite. It also has a strong focus. FemtoStar project, in addition to what I've already said, we have a strong focus on user privacy and security. And we have two satellite designs, one targeting the Pocket Cube form factor and one targeting the CubeSat form factor. The Pocket Cube is codenamed 𝗖cie, and the CubeSat is codenamed Horizon. But as far as this talk is concerned, the architecture is very similar. 𝗖cie is just a little bit stripped down. Really, nothing here is substantially different between the two. So this covers both. Before we talk about how FemtoStar works, it's worth noting that our mission presents a couple of unusual challenges. Real-time communications service as part of a constellation, you know, if you were doing store and forward, you might be able to tolerate a bit of a gap. You might be able to tolerate a satellite having to reboot. That's not really ideal for us. It's also worth noting that our satellites are designed for medium to long duration use if we need that and if they can stay in their orbit that long. They're designed to survive from sort of a radiation and battery wear perspective more than 6 years in service, and they're designed to support orbits of up to 1,000 kilometers, which is a pretty different radiation environment from, say, 450. It's also worth noting that rideshare launch, you know, if you were building a conventional communications constellation and you had the opportunity to be a primary payload, if you need to replace a satellite, you can do that. With us, we may have to wait for a rideshare, so we want to avoid opening holes in the constellation if possible. Not that it would make it unusable. In most cases, it's just a decrease in coverage angle, but still, it's something we want to avoid. So before we get into what we do to mitigate the problems of electronics in space, we should get into what actually goes wrong with electronics in space. This talk is mostly focused on single event upsets, which are sort of one-off radiation-induced glitches. Most of the time they don't leave lasting damage, although they totally can, like in a single event latch-up. And these can generally be mitigated with redundancy in systems, which is the focus of this talk. However, systems can also fail from a total ionizing dose, which is just, you know, radiation over time damages hardware and it can cause a lasting failure. Radiation will help you here when the first thing fails, but really the way you mitigate this properly is with shielding, or in traditional, you know, large satellites, you might have used radiation hardened parts. There are, of course, non-radiation related failure modes in space. There's rapid temperature and battery charge cycling, especially in low orbits. There's vibration on the launch vehicle, which isn't on the slide. And of course, any sort of diagnostics or fixes you may have to do, you're going to have to do remotely. There's virtually no opportunity to go up and repair your hardware unless you're these guys and have a space shuttle. So the traditional way that this would have been done on a large satellite is failure is not an option. You know, you have ultra specialized space grade hardware, really tightly controlled manufacturing, and, you know, really, really extensive, costly validation. This often means, surprisingly, that, you know, you think like, oh, space grade, super advanced hardware. Actually, a lot of the time it means that you're using relatively old hardware because it's probably already gone through your validation. It probably has flight heritage. And really, that might be worth more to your mission than the performance or efficiency that you might gain by going to something newer. For example, the chip in the picture here that we've included is the Rad 750. It costs $200,000, and it's really quite old by modern CPU standards, but it still gets used a lot today. Of course, it goes without saying that this is prohibitively expensive for FemtoStar and for many, frankly, I would say most small satellite projects to do an architecture entirely like this. There's also sort of the totally polar opposite way to look at this, which is failure is not an issue or failure is not a big deal. Where, you know, you could argue that some small satellites take an approach closer to this. The satellite here is $50 sat, which was a really cool pocket cube that used, you know, basically all simple off-the-shelf stuff. You sort of build it like a normal non-space grade electronic device would be. You probably still want to do a lot of additional testing of your hardware, but you're not choosing any really, you know, sort of space rated or special components. And for a lot of missions, you might be able to accept the short orbital lifetime, or you might be in an orbit where the radiation's not that bad. And this can be a really good idea. I mean, it's extremely cost effective. Especially, a lot of like IoT proposals, the network can tolerate a ton of dead satellites before it's really, really an issue for service. Unfortunately, for FemtoStar's mission, we can't quite go as far down this path as some small satellites do, just because, as we said earlier, our use case is a little bit unusual. We need a little more reliability than this offers. So what we need to do is option 3, which we like to call failure is not a failure. That does involve using off-the-shelf parts, and it's closer to sort of the way a lot of small sats are built than to the way traditional satellites would be built. But it's also really, really focused on redundancy. We massively reduce the number of potential failures of components that can cause the failure of the satellite. Single points of failure have been near entirely eliminated, and in some implementations of the FemtoStar architecture, completely eliminated. Of course, we can use off-the-shelf parts. Extended testing is still critical. And actually, our component selection is still very, very cautious. We have the highest available temperature grades of all our chips, flexible termination capacitors, and things like that. Off the shelf doesn't just mean go in the discard bin of your pick and place and start pulling chips out. There is still a very deliberate, cautious selection process that goes into it. But it means that, for us, an expensive chip is $100. For a traditional satellite, an expensive chip might be, the price of a house. Another really important part of our architecture is that satellites must attempt automated recovery if something goes wrong. And if that doesn't work, they must be, alive enough to allow for manual diagnostics and maintenance, even if there's some damaged hardware. Because even if things go really, really wrong and we can't save an individual satellite, the last thing we want is to not even know what's wrong and not be able to fix it on the next version. So there's a real focus on recovery and diagnostics. So before we can look at how to make FemtoStar reliable, we need to know what's inside one. There are 2 independent electrical buses. Well, one bus is supported, but that's less redundant. Most implementations wouldn't do that. There's 2, 3, or 4 service transceiver units, or STUs. They're independent from each other, and they have some internal redundancy. So, we certainly don't want them to fail, but they're not a super critical thing, especially in terms of, diagnostics to figure out what's wrong if one does go. There's obviously the typical sort of satellite stuff, the magnetorquers and sensors for ADCS. We've been talking for probably close to 2 years now with Applied Ion Systems about including one of their thrusters on board our satellites, and that would actually possibly be a single point of failure if we only had one thruster. There's also an optional backup telecommand-only thruster, but most importantly, there's the core of our satellite, the onboard computer, which is codenamed Helium. It's responsible for monitoring and attempting to recover other hardware. It serves as the central connection between other subsystems. And worth noting, because it's kind of in charge, it's running the show, it manages everything else on the satellite. It's the only complex subsystem on FemtoStar without an onboard twin, which means that design for Helium demands higher reliability than, say, design for the STU. So talking about Helium, I should explain what it is. It's a triple modular redundant computer. It has 3 units, each of which is known as a helion. They run in lockstep, that is cycle-for-cycle synchronization, and all of the units monitor each other. It's designed to be able to replicate its state from a working helion to a failed one in real time, and it achieves I/O through voting on outputs and sharing inputs. It also runs from multiple redundant clocks, which is a surprisingly deep topic we'll talk about later. Inside the helion itself is a lattice ECP5 FPGA. We like these things. Actually, let me show you one of these. This is where I like being able to have my composited into the video. It doesn't show up super well because of the background removal that I'm doing. I think it's probably to do with the chroma key because the board's green. But this is a bare board. We would have liked to have an assembled one here for you. Unfortunately, there were some delays in getting the boards. The fabricator actually messed them up and had to remake them. But that said, it is still cool to be able to show. I'll go back to my slides here. The Helion is relatively self-sufficient within Helium. It includes RAM, 24 megabytes of external RAM, which is the 3 SOICs you can see, and about 58 kilobytes of faster, more tightly coupled RAM on the FPGA itself. And it includes, we say a CPU core, but actually in reality it's 2. The FemtoStar has a payload processor and a spacecraft bus processor. And those are either RISC-V or our in-house architecture Libre VLIW, which is more something for down the road, unlikely to be on the first-gen satellites. Each Helion generates its own power rails from the bus. Those are the 3 power regulator chips at the top. They do not share their configuration flash, even though the ECP5 supports that. And it selects its own clock from multiple available ones. Yeah. So getting to redundancy now, to combining the helions together into the helium system, most people have a pretty intuitive understanding or some idea of the concept of redundancy. If one breaks, you have another. Makes sense. It's worth noting that redundancy is often talked about as having 2 of something. That allows one to fail if you treat failure as sort of it disappears, but it does not allow them to disagree and for you to still get a correct answer out of it. There's an old saying that I really like, apparently from nautical terminology, which was never go to sea with 2 chronometers, bring 1 or 3, as if to say having 2 chronometers that would disagree on the time on your ship was even worse than having just 1 that could be wrong. Having 3, on the other hand, as is the case in helium, allows them to disagree on outputs, because if there's 2 correct results and 1 incorrect one, it outnumbers it. Now, chances are you've probably heard all this stuff before, and there's a lot of explanations out there of triple modular redundancy that explain this, but the actual implementation of this is a lot more complex. And if you notice that I have about half my time left and I've already explained this, that's because really what I wanted to do in this talk is to explain some of the more real-world interesting details that FemtoStar has had to solve to make this actually work with real hardware. So redundancy in practice, okay, you think about you have multiple and they vote on outputs and you choose the right output. Well, okay, how do you get 3 computers to actually do the same thing 3 times and then check it? Well, you have to get them to run at the same time. This is called running in lockstep. Computers are theoretically deterministic. If they start in the same initial state and you give them the same inputs at the same times, they will have the same outputs. This is sort of a quote-unquote fragile thing. I'm cautious to use the word fragile because at the end of the day, it helps our reliability that we can do this. But any little difference that could appear due to some failure or whatever will take it out of synchronization. But it's worth noting that this isn't imminently dangerous. A faulty unit or a unit that loses synchronization is outvoted by the other systems. The computer will keep running, but a TMR system with 1 failed unit does not have redundancy against failure of another unit. You would need 5 units to be able to protect against 2 and be outvoted by 3. Recovery from this state without resetting the system is not trivial, and that's something we'll talk about later with regards to the status and replication engine on Helium. Even with 3 units, there still has to be something that decides which of your outputs is the correct one. And for that, there is the majority gate. It's also called a voter circuit, and it's a simple piece of electronics that, given 3 bits, decides whether the majority of them are a 1 or a 0. You actually have to be careful with it because you might think of it as a reliability feature, but it actually can create a single point of failure if you're not careful. After all, if the 3 helions feed a majority gate, but the majority gate fails, well, what's the point in having 3? Well, to that, we say, considering that the majority gates are independent of each other, a failure of a voter whose job it is to output to a certain subsystem is no more catastrophic than a failure of that subsystem, because being unable to talk to it is no worse than it not being there. It doesn't affect the other voters. On our architecture, at least, that would probably be sufficient on its own. But it's also worth considering how to make the voter itself reliable, and especially that voters can be extremely simple. You can implement them with 1 or 2 discrete logic ICs, even at really high data rates. Something like 74 AUC series logic can be, tiny little chip scale BGA packages and get, high data rates through discrete logic chips. Or even if you want to go even simpler than that, you can implement it in, say, pass transistor logic and discrete MOSFETs, which we've looked at. And there are advantages of that. They have large feature sizes, which are inherently a little bit more resistant to radiation. And most importantly, they lack the parasitic thyristor structure in integrated circuits that allows for radiation to induce a latch-up during a single event latch-up. Of course, if you want to go really over the top and maybe you have a non-redundant single point of failure device you need to control like a thruster, you could even go back to sort of the traditional satellite sort of school of thought and include a radiation hardened part just for that job and still, substantially save cost over having to build everything rad hard. I'll also just note this diagram here is a really good way to think about a majority gate, but it's not the only way one can be implemented. It's just a good way to show that, what it's doing is if any 2 inputs are a 1, the output's a 1, otherwise it's a 0. In reality, it can be implemented any number of ways. So getting back to the actual problems of implementing this in the real world, the first of these is the clock. In order to maintain lockstep, all of the units have to run from the same clock. And you might think, well, okay, if you have to have a single shared anything, including the clock, well, that's not very redundant. That could be a single point of failure. You might think, well, okay, if majority gates are so good at choosing the right output, just have 3 clocks, and if one breaks, the gate will pick the right ones. Unfortunately, you can't really do that with clocks. Maybe in a simulation it would work, but in the real world, any minor phase or frequency difference between the clocks is going to result in an output that's totally unusable. You could also imagine introducing some kind of a clock supervisor that could detect a clock failure and fail over to another one. But unfortunately, such a supervisor also becomes sort of a central point of failure that you probably don't want in your design. Thankfully, there is a solution that doesn't require this. If you feed all of the clocks to all of the helions and let them choose, doesn't really matter which as long as they choose working ones, as long as that choice is deterministic, and as long as the helions will all choose the same clock in the same situation, they will all be running on the same clock signal, even though there is no one canonical clock signal that is being given as the real clock to all of them. Now, you could still ask, what if there's a failure in clock monitoring? But because we've delegated that task to the helion, I mean, it's no worse than a failure of anything else on the helion, which TMR protects us against. The second problem is system monitoring. You want to know when you're running this thing, either as software or just as someone operating it from the ground, what is the status? Has unit 3 failed? How many ECC memory bit flips has unit 1 seen this morning? So you want to be able to have that monitoring. But it's also important that, again, you have to have the same inputs for the same outputs. So a unit can't know which unit it is, lest that affect its outputs. You could imagine introducing some sort of a supervisor or a management unit that would monitor all the units, but again, that's a single point of failure. So it's a little bit like the clock. What you actually have to do is delegate to the helions. Our solution expose the unit number only to a part of the helion. We'll say it's hardware, but really it's some Verilog code on the FPGA that we call the status unit. The status unit is the only part of the helion that's allowed to know its unit number, but it combines this unit number with information from the other helions to form and generate a status of the entire system, including all of the helions. It then exposes this system-wide status to its host processor on its helion, which means that all of the helions, their status units will resolve the same things based on different information, based on knowing their different units, and all of the CPUs will see the same thing from the status unit, so you don't have the opportunity to lose sync. Second to last, problem 3, detecting failure. Majority gates will prevent faulty outputs, but at least not without modifying the circuit further. They will not alert you to a failure. You could definitely make one that would, but especially when you're doing it in sort of really simple hardware, you don't really want to make it more complex. And also logic failures, especially, considering that FPGAs are made of RAM, 1 bit flips in a LUT, and all of a sudden, as I said in the title, 2 plus 2 equals 262,148 in what is supposed to be a perfectly good adder. So you need to be able to detect these internal failures, even if they don't affect the output. And when they do affect the output, you still need that detection because the majority gate won't tell you. So the solution is to have the helions sort of prove to each other that they are still working. We do this with what's called a state check bit. We generate based on all kinds of internal state from the helion, the program counters, the operands that the CPUs are working with, stuff in the registers, and some counters that exist specifically for state checking, a state check bit, and we provide that to the other helions, to their status engines. Status engine does its thing, forms the sort of cohesive single system image of status, and then based on it counts, and if you have millions to billions of correct state checks after that many cycles, the status engine in the other helions will deem the helion that they're looking at to be working. And you might think, okay, millions to billions of cycles, that's got to take a long time. But actually, at the clock rates we're working with, that's realistically only a couple seconds, right? And then finally, there's replication. When a unit fails, you need to try to bring it back before another one fails too, because again, you're only protected from one failure at a time. So after a helion is recovered, however that happens, the watchdog resets it, the other helions power cycle it. Maybe in a really extreme case, there's damaged hardware in the FPGA fabric, and ground crew need to send up a new bit stream that avoids using those gates. Again, that's why we mentioned the reverse engineering of the ECP5 is really important to us. And then once the helion is brought back up, whoever that happens, state needs to be transferred back onto it. This is trivial if you just reset them all, but to do so without interrupting service is kind of hard. The solution is what we call the status and replication engine. As helions, the other helions, the working ones, run, it shadows their memory writes to the target helion that's being replicated onto, and unused memory cycles where the working helions are scrubbing their memory also replicate across the scrub data, so it slowly builds up a copy of the memory on the running cores. Once all the memory is replicated, the working units dump their registers, which get replicated across, and the target is started, and you have a happy 3-unit FemtoStar Helium running again. So that's been my talk for now. Thank you. I will take questions if time permits. Otherwise, I've been Ethan Boicey from the FemtoStar project, and you can find more contact info at femtostar.com/about.